Hello, my name is Jorge Leon from Texas A&M University. I will present work done in collaboration with Professors Ek-Pung Chu and Lu Hei Lee at the National University of Singapore. The presentation describes a new methodology for AGV routing with deadlock detection for large-scale AGV systems. The work is motivated by autonomous vehicle routing problems in modern automated container ports. Modern ports can handle more than 35 million standard containers or TEUs. Thousands of ships can be in the port at any time, and ships arrive or depart every 2 to 3 minutes, linking the port with several hundred ports around the world. The AGV fleet may consist of thousands of vehicles, resulting in large-scale and dynamic operations, requiring frequent updates of the AGV routings. Furthermore, large vehicles are used and the real estate is costly or unavailable, hence, the AGV system may be more deadlock-prone than in other application environments. The AGV routing problem. Given a transit layout, a partially ordered set of requests, and a fleet of vehicles V, the problem is to specify all the routings needed to fulfill the requests. A routing specifies the timing of all move events by the AGVs in the transit network. The objective is to maximize the total sum of completion times, such that routings are conflict-free and deadlock-free. Unique to this work, is the consideration of the assignment of vehicles to requests as a decision variable in conjunction with the routing and deadlock detection problem. A capacitated digraph, termed here the Capacitated Transit Network or CTN, models the transit layout. Shown as a section of the transit layout is decomposed into resources, such as lanes and junctures. Each node in the network is associated with a transit resource with two attributes, capacity and usage time. The resource capacity represents the number of vehicles that can safely use the resource simultaneously, while resource usage time represents the minimum time required by a vehicle to safely use the resource. These two attributes facilitate high-level control of collision-free and uncongested transit. Nodes in CTNs can hold more than one vehicle, resulting in a smaller and simpler network when compared to existing models to ensure collision-free transit. The model is scalable since it can be used to represent each aggregate resource decomposed into its constituting resources. Given a subset of requests, we determine the vehicle request assignments and paths for each request. In turn, a path network is formed where nodes represent move activities in a path, and arcs represent precedence relationships induced by the corresponding path and vehicle assignments. The path network representation allows solving the AGV routing problem using extensions of the well-known resource-constrained schedule generation techniques. Routings must also be deadlock-free. In this work, we consider only cyclic deadlocks. Shown are nodes A, B, and C in a digraph, each with a capacity of 2. It can be observed that 3 cycles with vehicles waiting for the next resource unit to become available, so they can continue moving. The instance shown is not deadlocked, since a unit of capacity in node A will become available after some waiting, breaking the rest of the cycles. The system would be in deadlock if the capacity of node A was 1. Using CTNs complicates cycle detection since it is not sufficient to detect just elementary cycles. We derive deadlock conditions useful to detect, resolve, and avoid deadlocks. Briefly, given a cycle at time t, all nodes must be active with a vehicle. Vehicles in the nodes must be waiting for the next node in the cycle. The remaining capacity must be 0. All units of capacity must be involved in a deadlock. To facilitate the analysis of cycles in a capacitated digraph, we transform the transit network into a connected acyclic and transpose graph, or CATG. A CATG is formed by connecting a DAG and its transpose by pairs of switch arcs. Cycles in CATGs may only form through pairs of opposing switch arcs. We develop a procedure to find all elementary cycles between pairs of switch arcs in a CATG, and prove it has O(n) to the third power, worst-case runtime upper bound. Cycles in CATGs may form through more than one pair of opposing switch arcs. Class omega cycle is defined as a cycle in a CATG formed through k pairs of opposing switch arcs. We studied 2 approximations. The first approximation assumes there is a deadlock if a class omega-1 cycle is detected. This approach is optimistic, assuming only this type of cycle will occur, but possibility failing to detect other types of cycles. This approximation can be performed in n to the third power. The second approximation assumes there is a deadlock if any elementary cycle is found. This approach is conservative, guaranteeing all deadlocks are detected, but possibly overreacting with false alarms. This approximation may require exponential runtime. The CATG decomposition allowed us to derive several probability upper bounds as a function of the AGV problem parameters. In particular, the probability that a cycle with a given maximum length produces a deadlock. This probability allowed the theoretical estimation of the probability that deadlocks will occur as a function of system parameters. To the best of our knowledge, this is novel in the related literature. We also developed deterministic and expected worst-case runtime upper bounds for an AGV routing with deadlock type 1 detection procedure. The bounds derived for the static and dynamic routing versions are polynomial. Runtime estimates using the derived bounds suggest the approach is promising for the real applications motivating this work.